So can someone help me by telling where did we stop in the last class? I remember we completed, okay, I had to share and show you the solid state. Okay. So instead of drawing, I just thought I can help showing this. See, you can see that this is the simple cubic, the first one. Okay, so this is the simple cubic in which we only counted the 4 corners here and 4 corners at the bottom, which actually includes all the corners. If you look at the body centered, we are including corners and also one center of the whole cube, which is the units, which is of the unit cell. Look at the third one. You have the face centered cubic unit cell, which includes 6 of the faces that are pink in color, and the others are corners. So if you see in simple cubic, we have only considered the corners. In body centered, it's the body center plus the corners. In the face centered, it's face centers plus the corners. The next I wanted to show was this. So I hope you can see the screen. You can clearly see these are the lattice points that I mentioned in the previous class, and also the unit cell. This is the unit cell. Okay. So this is the unit cell. Next, you can see the lattice points. See, you look at the unit cell. In this, the transparent things actually show you the whole crystal, in which we are telling that each of the cube or the cuboid is the single unit cell. Okay. So again, see, you can see how is that the points are being contributed. There's no space as such here. It is like a full sphere. We assume that there are so many spheres, and in the simple cubic lattice cell, you can see there are 4 on the top, 4 on the bottom, and each of the cube, the sphere present here, is not only shared by single unit cell, but also will be shared by others. We'll come to this. I want to show the monoclinic. Yeah. So you know the simple cubic, face-centered cubic, how it looks like, body-centered. Please ask me a doubt if you don't understand. Okay. Yeah. See, yesterday we have written a table where I mentioned about cubic, tetragonal, orthorhombic, all of these types of unit cells. I have also mentioned the axes and the angles present. I wanted to now look at the same and the table. You can see a simple in the cubic, the 3 possible unit cells are the simple, the face centered, and the body centered. And I also showed you how the axis and the angles are related to each other. If you look at the tetragonal, you can see the difference between the cubic and the tetragonal type of representation. You can see the second one, which is tetragonal, looks a bit like a rectangle. The above is a cube. So these are just different, different types of unit cells with different shapes. If you look at the orthorhombic, these are the possible things under them. Look at the monoclinic. It's like a slight slant rectangle. Look at the triclinic. Look at the hexagonal. So all of them are different. If you don't need to exactly remember, but I want you to know that you have to understand that each of them here are differently arranged and the shapes are also different. The different lattice system pictures are here. let's look at some other picture also for a bit better, because the before I felt it showed some of them like same. Sorry. Seema, this is a bit more clear. Cubic looks like that. The rhombohedral looks like this. The hexagonal looks like that. The tetragonal looks like this. The orthorhombic is like this. Monoclinic is this. See, these are like trays and all, you can see. You don't need to remember the pictures much, not on the priority, but if you remember all the other values, that is the most important thing. If you want to take a snapshot of this, maybe you can. Or if you want to draw, I don't know, I'm bad at drawing. I can't draw exactly like this. If you all can, you can. So please take a screenshot now. Further, when we are talking, you might understand it a bit better. Let me know if I can stop my screen share. Can I? Screenshot pictures, whatever for reference. Or if you have the textbook in which all of them are mentioned, then it's fine. Okay, then as I haven't gotten a response, I'm assuming it that I can stop my. So I've given you the table, and I also give you, these are called the Brevis space lattices, and they all have different systems, different a type of possible unit cells for each representation and different kinds. Now let us understand certain rules that you have to follow while you're actually calculating the number of particles per unit cell that I have shown you, now those spheres and all that which are cut. Okay. So the calculation of the number of particles per unit cell. Okay. First point under which you have this is an atom at the corners. Okay. An atom which is present at the corner. That means if you have this, and this is a cubic unit cell, and I say that there is an atom here, there is an atom here, there is an atom here, and there is an atom here. Similarly, an atom is there here, an atom is here, an atom is here, and an atom is here. So if you look at this atom now, this atom which I'm talking about here, it is the first rule is an atom at the corner is actually shared by 8 unit cells. So the contribution of this atom, the contribution of the atom at the corner to a particular cell, and that particular cell will only be 1 by 8. Why? As see this sphere whichever is there, this is cut like this. On top of this, one more unit cell this will contribute. Here one more unit cell. Here one more unit cell. Similarly, behind this there are 4 more unit cells to which this one atom is contributing. I hope you understood. So the first, so you can see that this atom is contributing 4, and the other half of the atom is going to contribute to 4 more like this just behind it. So one particular atom is almost like shared by 8 unit cells. So for one unit cell, the contribution only is 1 part of the 8 parts. Correct? So the second point is an atom at the face is shared by only 2 unit cells. Hence, so the contribution of an atom at the face of a particular cell is actually 1 by 2 because, see, look at this. I have a cube like this, ma'am. So on top of this, I put one atom here in between. So it is obviously half of it is considered for this one. And on top of it is one more cube and the other half is into it. That's it. So the contribution of the one on the face, similarly here if I have one, half is inside, the other half is covered by one more cell beside it. That's all. So contribution of a face centered is only half. For a corner, it is 1 by 2. Let me know if I can clear. So third point, an atom at the edge center, is shaped by 4 unit cells. 4 unit cells in the lattice. So its contribution will be 1 by 4 to any particular unit cell. To any particular unit cell, the contribution is 1 by 4. Similarly, an atom at the body center of a unit cell obviously belongs entirely to it as it is present in between the unit cell. So the contribution will be 1 to any particular cell. Okay. And a very important point that you have to write down here is the number of atoms per unit cell, okay, is in the same ratio as the stoichiometry of the compound. This point is going to help you to predict the formula of a compound, of any compound. Let us do the applications anyway, okay? We are going to use all of these points. These are just rules that we wrote. We are going to follow them. Let me know if you're done. Should we solve the questions? No. Okay. So now let us calculate for a simple cubic lattice that we looked at and considered as one of the 7 different types of the solid that is in the arrangement or the Bravais lattices. So the simple cubic lattice is going to contribute to the, okay, we first know there are 8 atoms at the corners. Okay, so we know that, first of all, what is it? There are 8 atoms at all corners, and you know, each atom's contribution is 1 by 8. When you have 8 atoms and each atom's contribution being 1 by 8, so the contribution, that means like almost like it has 1 atom. Okay, so number of atoms present in the unit cell is 1 after joining those 8 pieces. Okay, next when you look at the body centered cubic lattice or the body centered cubic thing, we know PCC has already 8 atoms at corner and 1 atom at body. So what is the contribution now? The number of atoms here will obviously be the 8 atoms which is at the corner and also the 1 at the body center. So the contribution is 1 plus 1, 2 atoms. This is for BCC. The same for FCC. Next for FCC. So you know for FCC what happens? 8 atoms at corner, 6 atoms at face or on the face, on faces. Now contribution is 8 into 1 by 8, which is 1. Half contribution of each of it out of 6. So number of atoms present in FCC will be 4 and number of atoms present in BCC is 2. So can I clear? Can I clear then? So let me now tell you how will you apply these to find the formula or to predict the formula of any compound. Okay, the question, let me write it. A compound formed by the elements A and B has a cubic structure in which A atoms are present at corners and B atoms are at face centers. What is the formula of the compound? I'll give you 1 minute for trying. You can let me know the chat box, the answer in the chat box. Okay, let me tell you how. So as you said, there are A atoms at corners. You know, contribution is 1A. B at face centers. You already know B at face centers is 8 into 1 by 8 and also half into 6. So it is 1 plus. Sorry. But it's specific, na? They only said B at face centers. So we don't need to include the corners. I'm sorry. So B at face centers. So it's only half into 6. They said A atoms are present at the corners. So for the same unit cell, when I already counted corners, I don't need to count the corners again. So if it's only FCC, I would have counted both. But then here it's face centers. So no atoms of B are, the number of atoms here is the 3. So the formula is nothing but AB3. It's an easy way to know the formula or predict the formula. So I'm clearing the solution. If anyone wants me to show anything, ask me to. So actually there are so many different types of questions that can be asked in this specific topic alone that you can see in the test that comes up. Let's do some questions because it's actually an important concept, that is the solid state. I would like you to try a bit for yourself. It's okay. It's actually absolutely fine to get wrong answers instead of not solving it all. So let us look at the other question. Potassium crystallizes in a body-centered cubic lattice. What is the approximate number of unit cells in 4 grams of potassium, where you know potassium's mass is 13? I'll just wait for 1-2 minutes like before for you to solve. If there's anyone who already completed, let me write another question meanwhile. You have an ionic compound, an ionic compound which is made up of atoms A and B, has a FCC arrangement. It has an FCC arrangement in which atoms A at corners, B at face centers. If one atom is missing from the corner, what is the simplest formula? So these are 2 questions I gave for those who already complete the first one. No one answered. See, you know that in BCC there are 8 atoms at corner and 1 atom in the center. Overall, it is 2. Okay. Let us actually look at the number of atoms which are present in 4 grams of potassium. You know, in 39 grams, it is 6.023. I'm just writing off 6 into 10 power 23 for calculation. In 4 grams, it is how much? It is just 4 into 6 by 39. Okay. So, number of unit cells here will be what? Whatever value you're getting here. Let me multiply 4 by 30. 4 into 6 is 24. 24 divided by 39, I got 0.6. Okay. I got around 0.6 into 10 power 23. Now what will happen? I'll have to divide this by 2. Because there are the value of number of atoms per unit is 2. So for these many atoms, how many unit cells will be there? That is 3 into 10 power 22. Or you can write it as 0.3 into 10 power 23. Anything is fine. This is the answer. If you have copied the first answer, I'll clear the first one, and second answer also I'll write it on the top as the question is there at the bottom. So can I clear the first one? This is a question which was asked in JEE mains. The question that I just cleared. So the answer for the third one, whose question is written at the bottom. See, so the number of atoms at the corners which used to be 8 has now become 7, correct? As 1 is missing. So number of atoms of A will be only 7 because 1 is missing. Now, what is contribution? Initially it was 8 into 1 by 8. Now it becomes 7 into 1 by 8, which is 7 by 8. Okay. Now the number of atoms of B are actually 6 at 6 different phase centers, but its a contribution is only 3. So ratio of A is to B is nothing but 7 by 8 is to 3. You can multiply both with 8. You get 7 is to 24. The formula you can write it as A7B24 in the options, and you can mark it. These are all JEE mains questions. I can also give you very simple questions like calculate number of all of it, but those you will be able to do if you do a bit complicated questions. So let me know if you have copied this. Is it very difficult to send a yes in the chat box because I write so much on the screen? Will it hurt a lot if you just tell yes in the chat box?
Done.
Contribute that much?
Done.
Come on. I got an answer from Adyasha and Tanish. What about others? Vishwanath, Ramchur and Shruti, can you just send me a yes in the chat box if you're done? Or understanding, or if you're copying, if there's any doubt, some conversation, please. I'm anyways not forcing anyone to use your mic and talk. At least through chat, if you can be conversive, like, what is the problem? Am I scolding all of you? Yeah, if I get a yes from all of you once in the chat box, let me go ahead with 2 more questions. Thank you, Ramcharan. What about others? Thank you, Shanath. The other questions, so many aren't required. You can do at the end once the chapter is done. Close packing in crystals. Close packing in crystals. Okay. So for us to understand the packing of the particles in a crystal, we have to assume that these particles are actually spheres, right? And we also have to assume that they're all spheres and all of them are identical in size. And how will the packing take place? The packing is going to take place, that is the packing of the spheres which we just mentioned, they take place in such a way that they occupy the maximum available space. Okay, that is the closed packing. So how is the packing happen in this? The packing of the spheres takes place in such a way that they occupy the maximum available space, and hence the crystal has maximum density. So this is only called closed packing. In the closed packing, we again have 2-dimensional and 3-dimensional packing. That is 2D packing. 2-dimension, how is the closed packing going to happen? So, in the 2-dimensional packing, when rows are combined touching each other, crystal plane is obtained. Crystal plane is obtained. But rows can be combined in 2 different ways. One, the particles, when they are placed in the adjacent rows, they show a horizontal as well as vertical alignment and form squares. So this is called square close packing. I'll show you that. I'll draw the diagram for it. Let me know if you're done copying this part. I need to done for sure. Okay, that actually tells me that you're done. Okay. I haven't received a single done. That means he's still copying, right? Only Adyasha is done, I suppose. You should wait for others to be done. So everyone else is still copying, correct? Ram Charan, Shruti, Tanishq and Vishwanath.
Done.
Done, ma'am.
So how is this now? For example, see adjacently, this is how I combine. Just below. So in this case, there is two ways. One is I can combine them in this way or the other one in this way. So the chance here, you call it a square closed pattern. There's no other shape that you can see. This is when you try to just combine both of them adjacent, when each atom is adjacently placed. The other one is when the particles in every next row, when they are placed in the depression between the particles of the first row. So the third row will vertically align here. The third row will be vertically aligned. Vertically aligned with those in the first row. This is called hexagonal closed packing, which is very important. So see how 1, 2, 3, 4, 5. So in between the spaces, there's one more, one more, one more, one more. In between the spaces, here again I have 1, 2, 3, 4, 5. If you look at this, the combination looks like 1, 2, 3, 4, 5. 5. So it's like a hexagon. That is why it is hexagon closed packing. If you look at this, here for every 4 atoms, you have a square, na? So we say the coordination number is 4 for this, and you are having 6 pairs involved in this hexagon. So the coordination number of the hexagonal closed packing is 6, and these are very important.
Done.
Are you done?
Yes, ma'am.
That's it about the 2D part. Next, you have 3-dimensional packing. The 3-dimensional packing. If you see in the 2D, the more efficient packing is given by hexagonal closed packing, as we try to minimize the spaces present. Okay. Now look at this. This is hexagonal. Can you clearly see if you have AAA on the top and let's say BBB and AAA is again similar. Can you clearly see there's a triangular space that is present? Okay, everywhere is triangle. 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 A triangle. A triangle. A triangle. A triangle. These are all triangular words in hexagonal packing. Okay. You can see these are all on top, for example. This is on top. This is at the bottom. 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 Stop. So what happens here now? To develop the 3D closed packing of the same hexagonal closed packing, because as we said that is efficient. So if the spheres in the second layer are placed over the spheres in the first layer, that means exactly like this, that is we have drawn. What happens when the second layer is placed in such a way that the spheres find place in the B voids of the first layer. B voids means B, B, and this B, and this B, and this B. Oh, I'm not writing this B. A. These are the B's and C's are here. C, 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 C. So what happens here? So find the place in the B voids of the first layer. C voids will be left unoccupied. Under this arrangement, no sphere can be placed in those small voids. Only half the triangular voids in the first layer are occupied by the spheres in the second layer. But otherwise, it's not possible. So what will happen here? You will try to place a sphere like this. Like a sphere like this. A sphere like this. Again, a sphere like this. Sphere like this. And sphere like this on top of it. Like you have some, and on top of it, wherever the space is now, they're trying to fill it with some more spheres. Again, like this also to happen, there are two more ways. What happens? Okay, I want to tell that you have a tray of eggs and on top of it, you're trying to place eggs. Imagine you have a tray and eggs, ma. In between you have spaces, you're putting eggs on top of them. So wherever you find spaces, they are taking that 1 layer, 2 layers, 3 layers, like how you put your books one on top of other. That is 3D. I have to show you a picture instead, no? Give me a minute. I want to show you a picture. So let me show you the picture, which actually has the 3-dimensional voids. Look at this. Tetrahedral void is this. Square packing is this. The hexagonal packing is this. Whatever, I just need the pictures. You can see the tetrahedral void. You have three, like a triangle, and in between you have space. To cover that space, you're actually putting one more sphere. So it has a tetrahedron shape in 3D. Look at the octahedron. You have three and you're trying to put three more on top of it. So this is octahedral. Okay. So it's very important to understand and try to visualize the solid state. So as I said, see, tetrahedral hole, whichever is there, you're trying to cover it by putting a sphere on top of it. Octahedral hole, you are trying to put 3, 3, 3, still you have a dot. This is octahedral. So this is how the hexagonal looks like. But the void is tetrahedral. Void is different. It's a space, unoccupied space. See, you can the coordination number here is, if you look at the, so if you look at this point now, so when this is there, anything which is beside this directly attached will be the coordination number. That's why it is only 2. This is coordination number. See, this sphere is directly attached to how many things, ma? 1, directly attached to 2, directly attached to 3, directly attached to 4. So the coordination number is 4. Look at this. This sphere is directly attached to 1, 2, 3, 4, 5, 6 around it. It's directly attached. So coordination number is nothing but that 6 for it. Right? Whichever are coordinating with all everything around it. So I showed you tetrahedral, octahedral. What else? To be more clear. I think pictures are really helpful in these things. Look at this picture, clearly shows you the tetrahedral and the octahedral voids. Tetrahedral is the one which has a triangle. Octahedral is like you have 3, 3, 3 and a space in between. Okay, so we will understand or write something about the octahedral, like sorry, the 3D voids, that is the tetrahedral, octahedral. Then we'll have to carry on with the packing fractions. We have some more details about the voids that we have to learn. Some questions that are to be done on each of the topic. And after the voids, we have how different structures like NaCl, how is it there? CSCl, what is the structure? Different structures, and in detail we'll have to read. I think whole week, the next coming week, we'll have same chapter. And I want to ask which chapter test do you read tomorrow? We have done chemical bonding. So should I give questions on chemical bonding then? I'll drop a message in the group today. So you might have the test on chemical bonding tomorrow. So let me post it accordingly. Okay. Thank you all. Good night. So your test for tomorrow will be on chapter chemical bonding. I'll also post that in the group. Thank you. And good night. All the best for the exam tomorrow. Thank you.